Welcome to this lecture on transition metal organometallic chemistry from principles to applications. In the last few lectures, we have been discussing a very important topic called transition metal carbene complexes. Now, these carbene complexes are designated by the formulation of this type M double bond Cr2 and contain a carbon which is sp2 type hybridization. Now, with regard to this transition metal carbene complexes, we have also discussed another kind of transition metal complexes that has CsP2 center, mainly transition metal aryl type of complexes, which too had carbon with a sp2 center. Now, difference between these two type of compounds are that in this there is only a transition metal sigma bond, whereas over here there are two kinds of bond, one is sigma, the other is pi. So, they contain transition metal carbon multiple bonds. And this is how these transition metal carbene complexes are different from transition metal aryl complexes, which too had a CsP2 type carbon center. We have also looked into various kinds of transition metal carbene complexes that are known, and they basically are of two types called Fischer carbene and Schrock carbene. In our last class, we have also discussed about the requirements or the properties of the metal center with respect to the formation of these two kinds of carbene, and what was discussed was that the Fischer carbene is usually formed for low valent transition metals, whereas Schrock ones are formed for high valent transition metals. Also for Fischer carbene, there is a heteroatom substituents on carbenic carbon, whereas for the Schrock carbene there are no heteroatom substituents on carbenic carbon. In our last class, we have also looked at the preparation used for synthesis of a Fischer carbene complex, which was by the reaction of lithium alkyl reagent on the tungsten hexacarbonyl compound, followed by alkylation with a alkylating reagent, resulting in Fischer carbene complex, which was first used for making this kind of transition metal multiply bonded carbene compounds. We have also noted that these carbene compounds are of extreme importance catalytically, as they are important species in olefin metathesis reactions, and which was recognized by the award of Nobel Prize as late as 2010. So, this is indeed is a hot area of research in contemporary chemistry. Now, in this lecture, we are going to look at some of the important applications, preparative methods for transition metal carbene complexes, apart from the one that we had discussed in our previous lecture. So, the next method involves protonation or alkylation of neutral acyl complexes. leading to the formation of the Fischer type carbene. A very good example starts with this rhenium Cp complex having NO, PPH3 and CH3CU moiety, which when protonated with triflic acid gives the following Fischer type rhenium compound. And here we see the rhenium is bound to NO PPH3CP and the carbene contain a heteroatom which is hydroxide as shown over here. The next method involves addition of alcohol to metal coordinated isocyanide complexes. This also is a very useful method for preparing Fischer type carbene complexes. So, a very good example of this is seen in this cis dichloropplatinum PPH3 CNPH when treated with ethanol produces this cis bischloro PPH3 carbene complex as shown over here. So, this is also a very useful method of adding this alcohol on this C triple bond N with the OET moiety binding to carbon and the hydrogen protonating the nitrogen to form this NH pH resulting in this carbene bound to the platinum. Another method is the alpha deprotonation method by Schrock, which was used for preparing Schrock carbene complexes. Here BCP tantalum dimethyl cationic plus when one of these alpha hydrogen which is over here, this alpha hydrogen is deprotonated by base sodium methoxide yielding methanol gives this carbene complex bis cyclopentadienyl CH3 double bond CH2. So, this is an example of Schrock carbene and was first prepared by Schrock. By this method way back in 1975. So, what we are observing is that there are few versatile methods for preparing these carbene complexes that can vary from fissured to the Schrock ones. Here is an interesting example for preparing Schrock carbene through intramolecular reaction, as is shown below. Me3C CH2 tantalum, three of these, and dichloride reacting with Li CH2 C Me3 eliminates lithium chloride, giving a monoalkylated compound. So, here of the 3 neopentyl group and 2 chloride, one more has added. So, now there are 4 neopentyl group, 1, 2, 3, 4 and 1 chloride still remains. Now, that interacts with this CH2 CME3 species such that this alpha deprotonation happens in an intramolecular alpha deprotonation, which is the hallmark of Schrock synthesis, occurs over here in a intramolecular fashion, resulting in this carbene complex along with generation of CME4 to give tantalum bis neopentyl chloride with this carbene that further reacts with another molecule of lithium CH2CME3, resulting in loss of lithium chloride and gives this Schrock carbene complex. So, this is an extension of Schrock strategy, but in an intramolecular fashion, giving rise to similar Schrock type carbene complexes of the type which are shown over here. So, the versatility of the Schrock's method of alpha deprotonation is observed not only in intramolecular fashion, which is shown over here, but also in intermolecular fashion, which was originally used for making Schrock carbene complexes. Hydrater abstraction is another very good method for preparing carbene complexes, and this hydride abstraction is usually done from the metal alkyl group. Is a good preparation, and that can be seen for this rhenium complex, which when reacting with pH 3 trityl cation in dichloromethane, this trityl cation abstracts hydride from MCH3 moiety to give the corresponding rhenium complex having rhenium bound the CH2 moiety or carbonic moiety. This plus CH pH 3. So, this is a complementary strategy to the one that Schrock used, where it was alpha proton abstraction, and in this case this is alpha hydride abstraction. So, this is an example of alpha hydride abstraction to give a carbene complex, whereas Schrock had reported alpha proton abstraction to give a carbene complex, and that is known as Schrock's method. So, what we are seeing is that the versatility of formation of this carbene not only by an hydride, but also by an proton from the alpha position of the metal alkyl bond that results in this carbene formation. Another method of making carbene stems from the reaction of carbonyl metalloids and geminal dichloroalkenes. And this is shown by reaction of Na2Cr CO5 plus pH ClCl pH at minus 20 degrees centigrade in THF, that results in elimination of 2 NaCl, giving the corresponding carbene complex of the one that is shown here. In this case, that this carbonyl metallate, the anion, was reacted with this geminal dichlorocarbene, where this NaCl is evolved from reaction of this metallate with the chloride, leading to the elimination of 2 NaCl and resulting in formation of this carbene complex. So, this also is a very interesting way of making carbenes. Another obviously is a very simple way of trapping free carbenes using on a metal metal bond, and this is a very clever way of intercepting free carbene reagents, which themselves are extremely reactive and very difficult to characterize or isolate, but this is a very nice way of intercepting them, thereby proving their existence. So, this method involves C6H5 MnCO2 THF reacting with CH2N2, which eliminates the dinitrogen to give this binuclear bridging dicarbonyl cyclopentadiene manganese complex plus the dielephanic complex bound to the metal. Obviously, this olefin complex is formed by recombination of the two of the carbenes to form the olefin, which is then found coordinated to the metal. So, that is the maximum product, about 92% of yield, whereas the intercepted carbene is only 8% of the yield, and this was reported first by Hermann as a method for making metal carbene complexes. Another important attribute of this method is that it provides a bridging mode of this carbene between two metal center. Another example of interception of free carbene has been reported for a osmium complex as shown here. And this when treated with CH2N2 yields PPH through an N2, giving this osmium carbene complex. Here the carbene has been intercepted by osmium to give this osmium carbene complex of the type shown over here. Carbenes can also be prepared from electron rich olefins. This was one of the earlier methods of obtaining these compounds, and these methods involves electron rich olefins The particular reaction involves C double bond C N pH N pH that reacts with FeCO5 minus CO gives CO4 FeCN pH. So, in this case what is observed that the FeCO fragment binds to the carbene, which is obtained by the splitting of this diolefin, resulting in formation of the carbene as shown over here. Another interesting method involves preparing carbene from n-heterocyclic carbenes or their precursor complexes. So, this is a very a new method of preparing stable carbenes, and they are obtained from imidazole based n-heterocyclic carbenes or NHCs. From NHCs or their precursors. N-heterocyclic carbenes or NHCs are called n-heterocyclic carbenes, and they are designated as this, where there is a heterocycle containing nitrogen atom. The nitrogen is substituted by two substituents, and then there is this carbonic centers. These are called n-heterocyclic carbenes. These are first reported by Ardengo, who by putting proper sterics could stabilize free carbene, and which was isolable and bottlable. Free carbene by Ardengo was isolable and bottlable and even structurally characterized. So, these carbene complexes when treated with metal precursors loses a L to give carbene metal complexes, and the same can be obtained from the imidazolium halide precursor by treatment with MLN plus 1 and LH, where this L deprotonates this acidic proton and gives the base NHC metal complexes, and L is a basic ligand that deprotonates this acidic CH. So, with this, let me summarize the highlights of today's lecture. In this, we have looked into various kinds of preparative methods that are available for preparing these highly unstable transition metal carbene complexes that involve the reaction of nucleophile to carbonyl complexes, as was done by Fischer, and other kind of method which involved alpha proton deprotonation, alpha hydride abstractions, then from diolefins, from electron rich olefins, from n-heterocyclic carbenes, and several other methods that were successfully used in preparing these transition metal carbene complexes. We have also looked at the strategies of Schrock, which involved alpha proton deprotonation not only in an intermolecular fashion, but also in intramolecular fashion, that was used for preparing these carbene complexes. There were various other kinds of addition reactions to our NC moiety that also produced carbene, the desired carbene complexes. Now, this gives us a brief overview on various synthetic methods available for preparing these very important catalytically relevant transition metal carbene compounds. And then with this I conclude today's lecture, and in the next lecture we are going to look up at the reactivity property and the bonding scenario that persists in these transition metal carbene complexes. Till then, goodbye, and I look forward to seeing you in the next lecture. Thank you.